Okay, so in triangle JLN, if LN is 9.6, what are LM and MN? Okay, so we know that LN is 9.6, and we want both of these pieces. Okay. Now we talked yesterday, or one day this week, we talked about how if KN is parallel to JN, we end up with two similar triangles, right, by angle A. And so, like, we can compare little triangle to big triangle, little triangle to big triangle, right? Don't forget about that, because I'm going to show you something else today, but that still applies, okay? So I want to find both of these pieces. So let's find LN first, okay? All right. So if I find LN first, what would I do to set that up? No. 5 represents this little piece right here. What's the whole thing? Is it's little triangle to big triangle. So the big triangle is 8, right? Okay, so the big triangle is 8. How would I set that up? 8 over 3 equals 9.6 over x. You guys do it so backwards from the way I would do it. That's okay, it'll work. So 9.6 over x, right? So we did the long side to the short, the long side to the short. Okay. So we cross multiply and we get 8x equals 28.8. And then if I divide both sides by 8, what do I get? I get 3.6. Okay, so this little piece right here is 3.6, which means that n is what? 6, right? Okay. So that's kind of what we did this week. All right, now, the next question is, are the sides divided into proportional segments? Okay, are these sides divided into proportional segments? So is the ratio between the two pieces the same? Is what I'm basically asking. Okay, so let's test it. How do I test it? 3 over 5 equals 3.6 over 6. So if I cross multiply, I end up with 18 equals 18. So are these parts proportional? Yes, they're proportional. They're both going to be in a ratio of 3 to 5. You can reduce that to be a ratio of 3 to 5. Okay. All right. Now, so this is what kind of leads us to what's called the side splitter theorem. Okay, and the side splitter theorem says that if a line is parallel to one side of the triangle and intersects the other two sides, then it divides those sides proportionally. Okay, so if this is parallel to this, then you can set up a proportion. A is to B as AX is to BX. So AM is to MB as CN is to NB. All right. And so this is called the side splitter theorem. Now, they don't have this listed as a theorem, but you can also work backwards. Okay. If you don't know that these are parallel, but I can show that these parts are proportional, I can then assume that the lines are parallel. So that's just kind of extra information. For what reason this doesn't list that, but that does work. All right. So if this line is parallel to this one, then these two parts are proportional to each other. Okay. All right. So what is the value of x in triangle PQR? Okay. So we want to know the value of x. Now, these right here are my parallel lines, okay? This right here, we don't really know anything about it. We just know that it's there right now. You know that it's there. Okay, so using the side splitter theorem, what can I do? Okay, not just 4, because something like this is not there. This is not there right now. Okay. So it would have to be 16 and what? 12. Okay, so how would I set that? 16 over x plus 2 equals 12 over x. So 16 is to x plus 2 as 12 is to x. Okay, so I cross multiply and I get 16x equals 12x plus 24. Subtract 12x from both sides. That gives me 4x equals 24. Divide both sides by 4, and x is 6. Okay? So my x is 6, which makes this now 8, right? And it makes this 6. Okay, so I did that using the side splitter theorem. Okay, now I want to find z. Now the thing you have to be careful about is that the sides are proportional, but you can't use that 16 is to 8 with the bases. You have to go back and use similar triangles, okay? So you would have to work with this triangle and the larger, okay? All right, and you have to go back to similar triangles. So with that said, what would you have? How would you set up to find z? 16 is to 32. 16 is to 32. That's an 8. Oh no, 34. Right? Where'd you get 30? This whole thing here is 16. That's the green. The whole thing is what? Isn't it 34? 16? 24. Oh my gosh. You have to go green to black. Yeah. The green is 16. The black is 24. Oh, this is the 30. Oh, because you said 16 is the 30. I was like, where's it getting the 30 from? Okay. No, not 16 is to 30. You could do 16 is to z as 24 is to 30. You could do that, yes. So 16 is to z as 24 is to 30. I'm not going to be doing it. I would have done 16 is to 24 and z is 30. Anybody else would have done that? Same thing. 16 is to 24 as z is to 30. You would get the same answer. Look. Cross multiply. We would get the same answer. Okay. Huh? Yeah, absolutely. Well, what they did here is little to little, big to big. That's what he did. I would do little to big, little to big. Okay. All right. So we cross multiply, and so we get 16 times 30, which is 480, equals 24z. Oh, the answer. Yeah. Okay. I thought you were telling me that was the choice. Yes, right. The answer is true. Okay, so that finds x, and that finds z. Okay, so I'm going to come back to y. Okay, I'm going to come back to y. All right. So I'm going to talk to you about something here, and then I'm going to come back to it. Okay. All right. Erase this down here, and then we're going to talk about something. Okay. So we said this was what, 8? 8, and this is 6, right? And then we found z to be, that was, alright, so I'm going to come back to y here. Okay. Now we want to talk about what a midsegment is of a triangle. We talked about what a midsegment of a trapezoid is. Remember, the midsegment of the trapezoid connected the midpoints of the two legs, and it was parallel to both bases, and its length was half the sum of the bases, right? Well, this is very similar. It's a midsegment of a triangle, and it also connects the midpoints of the two sides, okay? And it is parallel to the third side, and it's half of the third side. So if this was like, let's say 50, and this would be 25. So it's real similar to the midsegment of a trapezoid, but it's a little bit different, okay? So this right here is called a midsegment. Okay? And it connects the midpoints of the two sides, okay? And its length is half the sum of the third side. Now, I'm going to go back, okay? Y is 15. Who figured that one out? Okay, Ben and Zach. So, Ben, what did you do? This right here, what's this length right here? 12. What's this length? 12. And what's this is 9, and this is 9. So what is this? It's a mid-segment, right? Which means it's parallel also now, and it's half the third side. Okay? Alright? Okay. Why? Why we said this what? 15. Okay. Good. All right, here's some more. In the figure, XY and XZ are mid-segments of triangle RST. So, XY is a mid-segment, so it's parallel to this guy. And XZ is a mid-segment, and it is parallel to that guy. Okay? So, what would XZ be? Okay, 6.5, because it's going to be half of 13, right? Okay, what about ST? It's going to be 14 because the mid-segment is 7, so that third side is 2 times that. Okay, what about angle RYX? RYX, what about that? 124. 124. See how the red lines are parallel? And that axis, the blue line axis is transversal? So those are what kind of angles? Not corresponding. Alternate interior angle. We knew they were congruent, we just didn't know what their name is. Okay, good. Alright, so any questions on what I did there? Okay, we got one more thing. Oh no, actually that's... Okay, now, this is a corollary, because it's kind of like a little mini theorem off the theorem, okay? And it says, if 3 parallel lines intersect 2 transversals, then the segments intercepted on the transversals are proportional. So if you've got 3 parallel lines, okay, then these parts are going to be proportional to each other. So we've got like A is to AX as B, okay? You can even do like this to the whole. Like, you know, AB is to AC as DE is to DF, okay? They listed AB is to BC as DE is to EF. Like I said, you could do AB is to AC as DE is to DF. And there's different varieties. You could use the smaller part of the other part of the whole thing. You could even go across, like some of you like to do, AB is to DE as BC is to EF. That would work also. So when you have those 3 parallel lines cut by 2 different transversals, it breaks those transversals into proportional parts. So if this is a ratio of 2 to 3, what's this one going to be? 2 to 3 if you reduce it, right? Okay? All right. The reflecting pool is separated by walkways parallel to Lincoln Street and Jefferson Street. Okay, so here's Lincoln Street and Jefferson Street. So these are all parallel to each other. Okay? The city wants to add an additional tiling around the pool. How much tiling does X represent? How much tiling does Y represent? Okay, so I want to figure out what this X is right here. So what would I do? What'd you say? Somebody said something. Sorry. 24 is to 72, okay? So 24 is to 72 as X is to 60. Good. Okay? So we're going to multiply 24 times 60, which is 1440, equals 72x. And x is 20. Okay? So this right here, 20. Okay? Alright. Now we want to find y. So what are we going to do set up for y? 24 is to 60. Is to 60 as y is to 72. So what'd you say? Alright, so we cross multiply 24 times 72, 17, 28 equals 60y, and you end up with 28.8. on that. All right, now we have one last theorem, and this is called the triangle angle bisector theorem. I need you guys' attention here. If a ray bisects an angle of a triangle, then it divides the opposite side into two segments that are proportional to the other two sides of the triangle. Okay, now, a lot of people mess this up. It's not hard, but they kind of create their own theorem that's not true, okay? A lot of people think that if this is an angle bisector, that the opposite sides are equal, but that's not true. This theorem says that if you have an angle bisector, it breaks this opposite side into a ratio that's the same as the other two sides. So this is an angle bisector, so see how they do ux is to wx as uv is to wv. Okay? Look at the numbers that I have here. If I look at this, 12/16, what does that reduce to? 3/4. And if I take 6/8, what does that reduce to? 3/4. See? So this is a ratio that's the same as that ratio. Okay? I can also set my proportion up like this. Okay, here's my angle bisector, and I can say, okay, ux is to uv. So 12 is to 6 as wx is to wv. That would work also. Okay? And notice that would be like 12 to 6, 16 to 8. Those are the same two, right? Okay? So either however you set it up. So when you draw that angle bisector, it breaks the opposite side into a ratio the same as the other two sides. Okay? So let's do a couple problems here. What are the values of AD and DC? So I need AD and I need DC. Okay, this is an angle bisector, right? Okay, well, what do I represent CD with? Oh no, we don't want two variables. Well, the whole thing is 13, and from here to here is x. So what's this? 13 minus x. Okay? Alright, so remember, this angle bisector breaks this opposite side into a ratio that's the same as the other two sides. So how would I set that up? 10 over x equals 16 over 13 minus x. Okay, you could do that. You could have also done 13 minus x is to x as 16 is to 10. I just want to show you both ways, okay? If you look at it, when you cross multiply, you do the same thing, okay? Whichever way you're more comfortable with, doesn't matter. All right, so we're going to cross multiply here, so we get 130 minus 10x equals 16x. Add 10x to both sides. So 130 divided by 26 is 5. Okay? So my AD then is 5, and my DC is 8. Okay? Alright? Let's come over here. What should we do here? Again, we got angle bisector. Okay, so 3x plus 3 over 3x minus 7 equals 18 over 12. Good. Alright, so we cross multiply, we get 36x plus 36 equals 8 times 3 over 54x minus 18 times 7, 126. Okay? Alright, so I'm going to subtract 54 and 36. That gives me 18x. And then add 126 and 36, which is 162. And then divide that by 18. And so x ends up being 9. Okay, so x is 9. What are they asking me for? They're asking me for GK and GH, right? So I've got, what, 27 minus 7, that's what? 20. So GK is 20. And then 27 plus 3 is 30. Okay? Alright, so if I wrote this as a ratio, that'd be what, 3 to 2? Would this be 3 to 2 also? Total is 3. Okay? So we learned basically 3 things. We have the side splitter theorem. And so if you have a segment that's parallel to the third side, it breaks those sides into proportional parts. Okay, that's why they write it like this. And to me, that's kind of, the letters get all mixed up. That's why I sometimes do this, because this is a fraction, this is a different fraction, but it reduces to be the same. The x is kind of. Okay, the triangle mid-segment theorem, it connects the midpoints of the 2 sides of the triangle. It's parallel to the third side. And let's say this right here, if GH was 15, what's DF? 30, right? And if you have an angle bisector in a triangle, it breaks the opposite side into a ratio that is the same as the other 2 sides. Okay?